video lesson corresponds with sections 15.2 and 15.5 on your textbook on the strengths of acids and bases and calculating the pH of strong acids. I'm going to concentrate my discussion primarily on acids, strong acids, but the same concepts apply to strong bases. Now, strong acids, the strength of acids depend on the amount of ionization, which of course means the amount of H plus hydrogen ion released into solution when dissolved in water. It is not the same as concentration of acid, which refers to the molarity of the molecular species dissolved in water before it ionizes. And we'll see that contrast in a couple of slides. Now, for strong acids, you have what's called complete ionization. The reaction goes to the right in one direction. The reaction is favored, so shown here, the reaction moves to the right for hydrochloric. We know hydrochloric is one of the three strong acids that are listed here: hydrochloric, nitric, and sulfuric acid. And all three of those move in one direction only. They completely ionize. And that's nice and convenient because if we know the molarity of the HCl put into solution, we also know, because it goes to the right completely, we know the value of the H plus or hydrogen ion, shown here as hydronium. We know the value of that in molarity in solution. Weak acids, on the other hand, the reaction is not complete. It does not completely ionize and go to the right. So you have an equilibrium system gets set up. Shown here is carbonic acid. This is the fizz in your soda. It is primarily due to carbonic acid. And notice that equilibrium symbol in the middle here. An equilibrium is set up where you have both products and reactants in solution at the same time. So this acid, carbonic acid, does not disappear and go to the right. It does in part, so you get some H plus as hydronium ion in solution, but you also have the original molecule, H2CO3, still in solution. So all four species are in solution. Here's some weak acids listed: carbonic acid, citric acid, which is on warheads and Sour Patch Kids, citric acid, ascorbic acid, hydrogen fluoride, HF, hydrofluoric acid is also a weak acid, and vinegar, also known as acetic acid, is weak. Most organic acids are weak acids as well. Organic acids have some carbon chain out here connected to this thing called a functional group. And in particular, this one's called the carboxyl group. And a carboxyl group has this, here's the Lewis structure shown, has this one hydrogen ion that ionizes and goes out into solution. That's the species, the part of the organic molecule that creates the acid. Acetic acid is just a methyl group, CH3, connected to the carboxylic acid group, shown here. So here's the methyl group, and there's the carboxyl group right here. And this is the hydrogen ion that ionizes and goes out into solution. Now, shown here in cartoon, the strong acid, let's start here, totally ionizes. So let's say, for example, we put 5 moles per liter of HA, let's call it hydrochloric acid, A is the anion, into solution. It totally ionizes, goes to the right, creates 5 moles per liter of the H plus in solution. That is a strong acid. So everything, notice, in the beaker is ionized. A weak acid is not the case. A weak acid, for example, let's go with vinegar. You might put 5 moles per liter of HA in solution, and you only get 0.01 moles per liter of H plus. So most of the species does not ionize and stays as the molecule in solution, and very few of them actually ionize. So a weak acid has low ionization. Here's some strong and weak acids. I crossed this one off. That's perchloric acid because you don't need to know it, but notice here's your strong acids up on top, the 3 that you need to know. And some examples of weak acids that we've talked about right down here is hydrofluoric, there's acetic acid or vinegar, there's carbonic acid right here. So strong is not the same as concentrated. Those two terms have different meanings in chemistry, and same with weak versus dilute. A strong acid refers to the amount of ionization. Strong versus weak means ionization. Concentrated means the molarity of the species in solution. Here's an example. You don't need to copy this. But something like 0.1 molar HCl, relatively dilute solution, only 1/10 of a mole per liter. However, if you take the negative log of the H plus concentration, the negative log of 0.1 is 1.0. This has a very low pH. It's a strong acid. However, let's take a concentrated solution of a weak acid, 5 moles per liter of acetic acid or vinegar. And notice that's pretty concentrated, 5 moles per liter, but again, very little of that material actually ionizes. So you have a pH that's much higher. Remember, pH is logarithmic, so that's 2.5 orders of magnitude lower concentration of the H plus solution, H plus ion in solution. Now, calculating the pH of strong acids is relatively easy because it completely ionizes. That yield arrow goes in one direction, over to the right. So if we know the molarity of the strong acid that we put into solution, we also know the hydrogen ion concentration. As an example, what is the pH of 0.03 molar HCl? Well, if we know the molarity of HCl in solution, we also know the molarity of H plus because that material, again, goes to the right and totally ionizes. No more of this, the molecular HCl exists in solution. So then calculating a pH is relatively easy. You take the negative log of the H plus concentration, pH is 1.5. It's a similar, well, actually, let's show you this. What is the pH of 12 molar HCl stock solution? That's how I buy my hydrochloric acid to make dilutions of that for your labs. The molarity then of the H plus ion would be 12 moles per liter. What's the negative log of 12? The negative log of 12 is negative 1.08. So that's right. The pH of my 12 molar stock solution actually is a negative number. So the pH scale can go lower than 0, can also go higher than 14 for really concentrated solutions of a strong base. Here's another example. What's the pH of a strong base? 0.025 molar sodium hydroxide. Again, strong base, material totally ionizes and goes to the right. So if we know the molarity of NaOH, we also know the molarity of OH minus, 0.025. So there's the molarity of the hydroxide ion, 0.025 moles per liter. The POH, you take the negative log of the OH minus concentration. So we take the negative log of 0.025, we get a POH value of 1.6. And of course, pH is equal to 14 minus the POH, rearranged, shown here. And therefore, the pH of this value would be 12.4. And that makes sense because we've got a strong base in solution. We've got a very high pH, 12.4. Now, the situation is not quite as simple for weak acids. In weak acids, you have, well, I think I skipped a slide. Yeah, I did. In weak acids, you have incomplete ionization. The reaction does not go to the right. It goes a little to the right, and some of the material ionizes, but some, in fact, usually the great proportion of it does not. So you don't forget the equilibrium symbol, is this right here, indicates that all of those species are in solution at the same time. So you have some unionized material. For example, this is hydrofluoric acid, and you also have some that ionize and formed the anion and the cation, H plus, in solution. So you have to set up what's called an equilibrium constant. An equilibrium constant is very simply a proportion. It tells you how much ionization has occurred, what is favored. The forward reaction, which by convention, remember the forward reaction is to the right. So the forward reaction is this direction, producing products. The reverse reaction is to the left, shown here, to the left, so the reactants are favored. So Ka, the value of this acid ionization constant, tells you how much is ionized. Don't forget how we write equilibrium constants. This is all of next chapter's equilibrium. We'll get into more of the mathematics next chapter. But remember, simply an acid ionization constant symbolized by K sub A, K means constant in chemistry, is a proportion of the molar concentration of products divided by the molar concentration of reactants. And it is a constant proportion, meaning that the equilibrium system will adjust itself. If you put more products in solution, some will react and turn back to reactants and vice versa, so that this value is always a constant, is always maintained. Don't worry too much about that now. In our studies now, the acid equilibrium constant is symbolized by K sub A. And again, it's a measure of the amount of ionization. That's shown right here. We've already written down these notes, so you don't need to write them again. Indicates how favorable the forward reaction is. Here's what I mean. Something like a strong acid, HCl as an example. So here's HCl shown right here. That material ionizes, goes completely to the right, and therefore the concentration of products will be huge compared to the concentration of reactants. So you have a very big number over a very small number. And in this case, the value for Ka then would be really high, much greater than 1. In fact, much, much greater than 1. So you have mostly products over a tiny, tiny number of reactants. And therefore, the value for a strong acid or a strong base is very big. And the converse is also true. For a weak acid, however, you don't have a lot of ionization. So something as shown here, which is vinegar, it stays mostly as reactants. Yeah, sure, a little bit ionizes right there, but most of it stays as the molecule. And so you have, looking at our Ka expression, you have a very small number products over a very large number reactant. And so you'll have a decimal, much, much lower than 1, a tiny number. So let's see, what do I have here? Oh, and in addition, you can have Kb based associations as well. A strong base is, let's cross that one off. Don't count calcium hydroxide as a strong base. Sodium hydroxide, potassium hydroxide will totally ionize, and therefore the value of products over reactants in our Ka expression is really large. And a weak base, something like magnesium hydroxide or ammonia, does not have much ionization. So you don't have many products. You've got mostly reactants in solution, unionized species. So you've got a small number over a large number, or a decimal, low Ka value, low Kb value. Here's some examples of excuse me, Ka values. Notice hydrochloric acid right at the top. Hydrochloric acid is a strong acid, so the value for Ka is really huge, mostly products over a tiny amount of reactants that did not ionize. So it's 10 million, or 1 times 10 to the 7th. What that means is essentially only 1 in 10 million particles will not ionize and will stay as molecular HCl. And most of the stuff turns to H+. A couple of weak acids that we've talked about, here's carbonic acid, here's acetic acid, and notice their values, 10 to the negative 5th for lactic acid, or that is acetic, sorry, 10 to the negative 7th for carbonic. So the value of the numerator, the ions in solution, the products, is really small compared to the amount of unionized species, which is much larger. Don't worry about pKa for now. That's mostly an AP concept, but that's the negative log of the Ka value, just like we've learned. So don't copy this. Here's a quick example. Carbonic acid shown right here. There's the molecule dissolved in water, ionizes some H3O+, the hydronium ion. Also, you can symbolize that as H+ in your mind. And the bicarbonate ion is what's left in solution. Now, again, we just put concentration of products over concentration of reactants to get the Ka, the acid equilibrium constant. That's shown here, products over reactants. And remember this weird little trick, and it is it is cheating. We cross out the molar concentration of water in water. That's one of our reactants, so it's shown in the denominator right there. So we cross that out and we ignore it, so you get this as a final expression for the Ka, products over reactants, ignoring water. And remember from our previous table, it's a tiny number. Carbonic acid is 4.4 times 10 to the negative 7th, shown here. Okay. So what that means is that these numbers, the products, are incredibly tiny compared to this number right here, which is incredibly huge. So carbonic acid does not, look at the top, does not strongly ionize. It's mostly as a reactant and only a very little bit of product. So in summary, really all you need to know for now about acid ionization constants is this. It tells you the strength of acids. If Ka is a really big number for example, like HCl, you've got a strong acid because you've got mostly products. The material strongly ionizes and you have H plus and whatever the anion is in solution and not much reactant. Conversely, a weak acid is going to be incredibly tiny, 10 to the negative some number, and usually 10 to the negative 4, 10 to the negative 7th, or some smaller number, because it does not strongly ionize. Not much of that material is put into solution. I'm sorry, not much of that material ionizes. Depending, you can put a strong solution, meaning very concentrated, but not a strong solution. You can put a concentrated solution uh, having a high molarity, but the strength of the acid is not good. It's a very weak acid, not much ionizes. And that's all I have for notes for today. So you may work on the rest of your homework, which is written on Schoology for the remainder of the period. I hope to see you all tomorrow.